Hey everyone, so we're going to move on to our next unit, which is all about momentum. Now, momentum is actually very similar to the energy unit in the sense that, for the most part, equation wise and concept wise, it's very similar to the Regents course, where it covers a lot of the same stuff with a little bit more emphasis on certain things, as you'll see later. But for the most part, the big focus in this unit is going to be related to what's called the conservation aspect. Again, just like the energy unit. Just like the energy unit, we're going to start off first by talking about some of the basic definitions. We're going to start with talking about the definition for what's called momentum. Now, you've probably used it before in a lot of cases. You've probably heard it. In fact, in a lot of cases where you try to explain your reasoning for a certain phenomena, a lot of you actually use the term momentum, though, albeit you kind of used it incorrectly. So that's what we're going to talk about right now. What actually is momentum, and what does it mean when we say it? So, momentum, which I should point out, is represented through equations with a little p. Why is it represented by a little p? I don't know. But it's not represented by an m because that's mass. So momentum is little p. All right. And don't capitalize it because if you capitalize it, technically that becomes power. So momentum, little p, is a way we could describe the quantity of motion an object has and its tendency to stay in motion. Now, if you pay attention to the way that I phrase that, you may notice that that actually sounds very similar to the definition of inertia. Recall, inertia was the object's tendency to continue its motion, to resist changing its motion. If an object was at rest, if it has a high inertia, it requires a lot of force to stop it from being at rest, to start it to move, and vice versa. If an object is moving, it's going to take a lot of force if it has a lot of inertia in order to change whatever motion it has. Momentum actually is very similar to that. In fact, momentum is very similar to the concept of inertia, and it's also very similar to the concept of kinetic energy. In the fact that it's kind of related to a lot of those topics, but don't confuse the two. For the most part, you're not really going to be combining them. However, this is important in the concept of some of the regions questions you might see, where a lot of times they'll give you choices with a lot of masses and velocities, and they'll ask for which one has the greatest inertia. And a lot of you are probably going to accidentally think about momentum because, again, they're very similar in cases like that. So going back to this, an object has a certain amount of quantity of motion, has a certain amount of momentum. The more momentum the object has, the more force is needed to either stop it or slow it down. So again, it's very similar to this idea of kinetic energy and inertia in the sense that the more we have of it, the more force is required to take it away or to change it. If you have a lot of kinetic energy, you need a lot of force to do a lot of work in order to get rid of that kinetic energy. And if you have a lot of mass or a lot of inertia, it requires more force to change your motion based off of that inertia. Momentum, again, very similar. So, what are the things that we need to have in order to have momentum? Well, as I kind of hinted, it's very similar to the concept of inertia and the concept of kinetic energy. So, what are those two things have in common? It's going to be related to mass and speed. So, the equation for momentum is P equals mv. Mass times velocity equals momentum. Mass is represented in kilograms, and velocity is going to be represented in meters per second. So the unit for momentum is actually kilogram meters per second. It doesn't really have any fancy units like force and energy did. It's just literally these are the two units that we multiplied, so we multiply them in the units. However, I should point out that there technically is another appropriate unit, which you'll see later on why this is, of Newton seconds. You could use Newton seconds to also represent momentum. However, usually in most contexts, if you see momentum, it's going to be represented in kilogram meters per second. Now, one thing to note is this is multiplies, not divided. So I'm making sure not to say newtons per second. That's not the case. It's Newton times seconds or Newton seconds. This is kilogram times meters per second. All right. So let's do some practice questions. Pause video, work itself, and we'll go over in a second. All right, so they want the momentum of a car. They give us this mass and speed, so we just use our equation. Literally just plug in the number to 1,020 to find the momentum of the car. We get 20,000 kilogram meters per second. And then for the truck, We just take its mass and its speed and multiply, and we get 100,000 kilogram meters per second. All right, here's the next one. Pause the video, work itself, and then go over a second. All right, now you'll notice that this says linear momentum. You don't have to worry about that for now. As we'll talk about later, there are other types of momentum. There's other types of energies, but we'll talk about that as we get closer. Just think of this as the typical P equals mv. Just ignore the word linear for now. So they want the object's kinetic energy. Kinetic energy is 1/2 mv squared, which means we need a mass and a velocity. I only have a mass here, so what I can do is I can use this momentum to figure out what the velocity is. So I use the 6 and the 2 to get that the speed is 3. Once I have that, I can then use the kinetic energy equation, plug the numbers in, chug out an answer, and I get 9 joules. All right, the only other thing to talk about is total momentum. Now, this was something I didn't mention yet, but for the most part, momentum actually is a vector. As I said before, it's not mass times speed, it's mass times velocity. Velocity is a vector, therefore momentum has a vector. And in fact, velocity and momentum will always point in the same direction. So if you're moving to the right, your momentum's to the right. Easy enough. Just like how acceleration and force, net force, always point in the same direction, velocity and momentum always point in the same direction. But just like how we can have multiple forces acting on an object and we could find the total force acting on it and find the net force, we could do the same thing for momentum. If we want to find the total momentum of a system, what we can do is take all the momentums and add them together. Though because they're vectors, we have to make sure that we add them like we do vectors. We can't just do a straight addition. So if two momentums are acting in opposite directions, we subtract them. If they move in the same direction, we add them. And if they're moving at any other angle, we have to do some sort of jiggery pokery with SOHCAHTOA and um, trigonometry to figure out what the net total is. Now, why are we going to do this? We're going to do this for the whole concept of conservation momentum, as we'll see later on, where we're going to need to have multiple objects moving with different momentums and consider what the total momentum of the system is. So this is kind of how you would write it. Now, you wouldn't actually write down this equation because, like I said, it's not really an equation. It's just saying that, we can find the total momentum by adding up all the momentums. But like I said, we have to pay attention to the fact that momentum is a vector. So direction matters. All right, so here's the next question. Pause the video, works up. We'll go in a second. All right. So again, we have the pretty much the same problem as we did before. So we know what their momentums are. Now the question is, what would the total momentum be if they're moving in the same direction versus opposite directions? If they're moving in the same direction, we literally just take these two numbers and add them together, and we get that the total momentum is 120,000 kilogram meters per second. And if they're moving in opposite directions, we subtract them. I don't know which one's the going right, which one's going left. Doesn't really matter. So we just subtract them with 100,000 being the bigger one, and it would be 80,000 kilogram meters per second in the direction of the truck. Again, we're not really given a direction, so it's not like that matters. We just kind of want a rough idea of generally what the momentum would end up being. And that's pretty much it for this momentum stuff. Like I said, pretty straightforward. You have one basic equation and the idea that momentum is a vector that you would have to add and take care of direction. I will point out that as far as direction is concerned, though, typically momentum will only really you'll only have to deal with momentum in one dimension. So the object will either be moving in the same direction or moving in opposite directions. It's very rare that you will see ones where they're moving in perpendicular directions. It is possible that you might see it, though I would say that that's one of those um, uncommon to rare type questions. So I wouldn't really focus too hard on that. I might show a few examples in class later, but I wouldn't stress too much about it. Just focus on understanding the concept of momentum in one dimension before you consider two dimensions. All right, if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.